Hi, this is Tracking Mathematics and Statistics. We are at the part 4, which is probability and the softmax. In the last couple of sessions, we already learned that a model does not produce text. It produces something called a distribution of various probabilities, and that probabilities is something that we sample the tokens from and then generate the text from it. Yeah, and that's what we'll be learning today. Yeah, what systems help us generate the right output, and how calibration, all that is dependent on what we are trying to do as part of these mathematics and statistics. So by the end of this part 4, what we're going to look at is, hey, we will be able to read a distribution, not a point estimate. Yeah, we'll also name the 4 parts of bias, like your prior, your likelihood, posterior, and evidence. Yeah, that we'll look at. We'll also explain what softmax and temperature actually do. Yeah, softmax that restricts the output score between 0 and 1. Temperature tells you, hey, how much creativity do you need, how much diversity do you need. That's that knob. How do we differentiate, or how do we optimize for that? We'll look at answering the deterministic questions in 3 parts. Yeah, firstly sampling, floating point, and batching, and the model that's changing under us because of this batching, floating point, and sampling. Yeah, we'll be writing a decoding policy per surface, because at the end it's a very thin layer that we are writing on top of the existing model, the outcomes. So we should ultimately be able to say why confidence is not correct. Yeah, when a model gives us, I'm 90% confidence on this answer, why that alone is not sufficient for saying that it is a correct answer. And this is what our journey will look like. We'll start with the language. We'll understand what random variables are, what is an expectation, what variances are, 7 types of distributions. We'll look at it. Then we'll start with Bayes' theorem and how it is used under conditioning, how the chain rule is applied. Chain rule, if you remember, we looked at back propagation and so on. So similar style of chain rule. The base rate trap, what is a base rate? We'll look at it. Decoding, when we uh, send the token generation, on the decoding side we get text. Yeah, how does that happen? How logits are used, how softmax is used, what is the temperature, what is top k and top p? Many a times you would have heard people say top k and top p. What are they? We'll learn them today. The PM pass, how product managers should look at the whole thing. Your calibration, your deterministic outputs. Yeah, the decoding policy table, everything is dependent on whatever we are gonna learn today. So what are we saying? Yeah, we are saying, hey, learn the language, meet the distributions you will actually see. Yeah, that's what we are gonna do today. And one sentence that will make this non-optional is, if a language model was producing something, it is not producing text, it is producing a probability distribution over the next token, and then we choose that token based on certain policy or a framework. Yeah, everything happens from there. That is PM's argument. Now we look at 5 arguments. Why is it non-deterministic? Yeah, so when a system gives an output, it's giving a probability distribution of certain tokens with certain probabilities. So what happens is we are doing a sampling there. How much sampling? Based on temperature control. Why is it confidently wrong? Because it's not calibrated. Why is it our 99% accurate classifier filling the queue with junk? We look at Bayes' theorem and how it impacts. Should we raise temperature? Yeah. Should we make it more creative? That's distribution shaping. Is this 3% lift real? That's the sampling variability that we are looking at. So most PMs learn these as 5 unrelated pieces of trivia. What we are gonna do is, we are gonna take it as one subject, and there are many future sessions that are gonna come up which will be related to this. So understanding the relation, understanding the underlying foundation as a platform is important for us. And if this context, if the this session holds a context, all the future things are dependent on this. So we really need to tie this down together understand every term that we are gonna look at. So it all the future sessions become easier for us, and we are able to answer the questions that engineering team raises. When something fails, we are able to debug it with much higher clarity. And whenever we talk about LLMs, we are talking not in terms of determinism, but in terms of probability. So when we talk about probability, we need to really understand the language of uncertainty. Yeah, when we say uncertainty, we need to talk about what are random variables, what is an expectation, and the one number that's stopping us from shipping. Yeah, three nested objects. Imagine. Let's talk about space to begin with. Sample space is nothing but a collection of all the events that could possibly happen. Imagine if you are rolling a dice, the sample space is 6, as in the outcome is one of the 6 uh, numbers on top of the dice. Yeah, if you are trying to predict the next token from an LLM, it is the whole vocabulary, which is typically between 50,000 to 200,000 tokens. Yeah, and an event is any subset of that sample space that we are caring about. A random variable, it's a function that assigns a number to each outcome. Random variable is nothing but assigning a number to the each of this outcome from the sample space. It turns messy real world outcomes into numbers you can average and compare with. We looked at how tokens were embedded in vector space so that we could compare their associations, we could compare their relationships, we could understand the closeness of those using cosine similarity and everything. So random variable is nothing but assigning a number to each of those outcomes. So the next token that we are trying to predict is actually a random variable. Yeah, and so is the latency of a request, the cost of a user, the score of an eval case. All of these are random variables. And how are these random variables? There are two types of them. One is a discrete, one is a continuous. When we say discrete, they are in typical numbers. For example, countable outcomes like just say next token, click or no click, ticket category, support classification. All of these are discrete types. Whereas in continuous, there is a scale which is continuously uh, giving you numbers, and it could be in milliseconds, cost per request, cosine similarity, which is on a continuous number scale. Yeah, here it is by probability mass function, here it is by probability density function. Yeah, so in discrete we only say, hey, the probability of each outcome, how do we measure? Using a probability mass function. And all these probability mass functions, they actually sum to 1. If you know a particular token and its probability can be calculated, you can sum the all the probabilities and they will all sum to 1. That does not happen with probability density functions. Yeah, which is why latency, everything is quoted in percentiles rather than a probabilistic number that can be summed to 1. And that's the density trap also that we are talking about. Yeah, if a chart's y-axis can exceed 1, then what will we do? Yeah, we are looking at a density and not a probability, because probability is typically between 0 to 1. And when it becomes the density, if you want to measure the density, we look at area under a region and never at the height of a particular point. So your AUC, which is area under curve, all that become important for us. Yeah, and where this bites in practice is, whenever we are trying to read the model confidence plots and drift dashboards, teams actually read it like a tall peak as high probability. Hey, we've achieved this. Uh, Ideally, it should have been a high density over a narrow interval. That's what we should be ideally measuring. Yeah. So, what should we inculcate as a habit is, before interpreting any distribution chart, check whether the axis is bound by 1. If not, take it as a density and consider area under curve and so on. So any y-axis above 1 is a density. Ask for the area, not the height. So imagine there is a support ticket that we want to classify and categorize, and reduce the cost of categorizing these support tickets. Imagine AI resolves 60% of the tickets on its own and it saves $12, whereas 40% it does not resolve, so approximately it's costing $3, uh, because we have to take it to a human and it's not $12, now it is reduced to some extent and so on like that. So $6 per ticket is what we are trying to say. So what are we trying to say? That is, our linearity is the useful part. Whenever we can split two events happening x plus y, which sum is 100%, we can split them and calculate individually and then sum them up, like e of x plus e of y, which is the linearity part. Yeah, stage wise we can calculate them separately and then correlate them. So the costs add that risks do not. Yeah, linearity of expectation always holds. So variance of any linear variance only adds under independence, as in these two are independent actions, which is the subject of the next slide. Yeah, because all your bias, everything expects that there is a dependency between these two. But here, since these two are independent events, we can say e of x plus y is equal to e of x plus e of y. So two configurations that share an average is, imagine the high variance that we are talking about. Yeah, one produces occasionally brilliant answers because it's very uh, creative in mind and so on. Whereas occasionally disasters because we want a deterministic answer. Yeah. So the low variance one could be reliably fine because there is very little variance in answers. It is reliably fine. So imagine two cases. Yeah, consumer brainstorming tool where a customer is trying to ideate on or create mind maps or trying to generate new ideas for artwork or any of that stuff. In that case, high variance may be the product. But for a medical summarizer where deterministic answers is the highest requirement, high variance could be a lawsuit because we have generated too varied an answer. Yeah. So variance only adds under independence. Like we said here, when the two events are independent, we can add the variance with them. But if they are dependent, we cannot do that. And that brings us to the seven distributions that we are going to look at. Seven distributions are split into 4 and 3. 4 is when we are trying to evaluate, 3 when we are trying to operate. Yeah, we do not need the zoo, as in we do not need 20, 30, 100 distributions. We only need these 7. Yeah, and we can typically see them in dashboards also. Bernoulli's distribution. Bernoulli's distribution is typically coming into play when we have one yes or no event. Typically, did the system fail? Did the guardrail fire? Did user accept the suggestion? These are yes or no events. So we can do that with a probability, and that's where Bernoulli distribution comes. Binomial distribution, successes in n independent trials. We've learned this before. So imagine we have 500 evaluation cases. In that, how many passed? And if you put them on a distribution, they will typically look like a binomial distribution. Categorical, one draw from k options summing up to 1. Sum is always 1 here. Yeah, next token prediction, also intent classification and routing, all these are examples of categorical distribution. Gaussian distribution, we know, if you take the mean of the various values and put them on a distribution, they look like a bell curve. Yeah, this is the averages of many things. Rarely raw latency is there, uh, which can be shown as a Gaussian distribution. When we operate, these are the three distributions that we could meet. One is a Poisson, which counts the number of events in a fixed window. Yeah, if there is a window and there are a number of events in a particular window, Poisson distribution could typically represent that. Where it shows up in is in use cases like requests per second, incidents per week, capacity planning over a month or a quarter, and so on. Exponential distribution, where we are waiting time between events, memory less, and so on. Imagine user sends a request and we have to retry. When we retry, we can't do it every second because it will do too many calls. what we could do is we can increase the waiting time, or increment the number of seconds that it queries. It can be done in the ratio of 2, 4, 8, and doubling every time, which is like an exponential case. Yeah. Log normal, right skewed, long tail of large values. When we look at latency, tokens per request, cost per user, this is when log normal distribution comes into play. Yeah. We as PMs don't need to derive all these distributions that we looked at: Bernoulli distribution, binomial distribution, categorical, Gaussian. We don't need to derive them, but what we need to do is understand why these distributions are used in these various places, and what do they mean. Yeah. Because indirectly we are looking at costs. Imagine we don't understand latency, the number of tokens per request, which are of the log normal distribution. We might not calculate how much money is being spent and so on, which is actually important for a product manager. This brings us to the central limit theorem. And if we do not understand this, we will not understand the economics behind LLMs. If we average enough independent samples of anything, the averages become approximately Gaussian in distribution, like a bell curve. Yeah. Even when the underlying things is not. If the independent samples, there are independent samples, themselves might not be normally distributed like a bell curve, but when we take their averages, yeah, we average enough independent variables, their distribution, the distribution of averages, will always look like a bell curve. And this is one reason that these statistics work. And we look at week 5 and 6 that we'll be building around the intervals and the ugly metrics that we will be using. We'll be looking at p p values. We'll be looking at the intervals and so on. So that's where this ugly metrics come into play. The misreading stated carefully, the CLT is about distribution of the average, not the distribution of the actual raw data. So in practice, what we are saying is your latency per request will never be Gaussian. But if you take the mean or averages of those latencies over 10,000 requests, that could be a proper normal distribution. So imagine when we talk about latencies, imagine the spread of latencies like this. Top 50 percentile has 400 milliseconds. 90 percentile has 1200 milliseconds. P95 is 2100 milliseconds, which is almost 2.1 seconds. P99 is 8.6 seconds. Yeah, that's how long it is for 99 percentile. As in 1% of the people will actually be waiting for 8.6 seconds. Yeah. So uh, the worst case guarantee is 8.6 seconds, and because customers will be looking at it, and our mean says nothing about what is the worst case performance. 900 milliseconds, it's nowhere. Somewhere in P75, P80, somewhere P800, P80 maybe. That's where 900 milliseconds come into play. Yeah. But this small fraction of users towards the end, they come to dominate the total cost that we will incur in terms of performance. So we need to consider this. Yeah. And we need to show users these, not just the average will look always good, but when we write SLOs, which is service level objectives, we need to ensure that we don't write mean, rather we write it in percentiles. Yeah, that's what they are saying. Percentiles are nothing. For anything cost or latency shaped, always ask for the distribution, not the average. The mean of a heavy tailed variable is not a summary, it's a distortion. So always ask for SLO. What we need to write instead, like P95 under 2 seconds, P99 under 4 seconds, and so on. And then ask what the tail is made of. How far is the tail? How thick is the tail? Yeah, do we have long outputs? Do we have cold starts? Do we need to do retrieval or queuing under load? How do we need to solve the problem? Because a fix is different for each, and the diagnosis matters more than the number. How do we diagnose? How do we fix? How do we deliver? Yeah. And that brings us to part 3, which is conditioning and bias. And This is interesting because many times the model will say I'm 90% accurate, 99% confident, and so on. And that does not mean that it is giving us correct answers. And that's what we are going to look at here. So imagine reading about bias theorem. Bias theorem case that hey, if there is a probability of P, where probability of A given B event, uh, imagine it like hypothesis and your evidence collection. In that scenarios, we could calculate them independently, and since they are dependent on each other, unlike independent events, they are dependent on each other. We can calculate their probabilities to understand what does that dependence mean. Yeah. So if there was independence, P of A given B would have been equal to P of A in simple terms, but that is not the case. Now, how do we calculate these individually? We understand that P of individual weights that we have in an autoregressive model, we can calculate the probability of weight 1 multiplied by probability of weight 2 given the probability of weight 1, and so on until we have probability of Wn given that we have all the other probabilities of other weights uh, that needs to be calculated. And this is not an analogy for language modeling, it is language modeling. That's what we are looking at. So prompting is all about that conditioning, because we are not instructing the model. Yeah, we are choosing which slice of the distribution it operates in. Yeah, the prompt and the retrieved context are the conditions, they are not commands. The prompt, let me repeat that, the prompt and the retrieved context are conditions, not commands, because system LLM does not understand commands, it understands only conditions. Prior text, the prior text is your prompt and the retrieved context. Yeah. So that framing makes prompt and context engineering a probability discipline rather than a folklore one. We understood this. It also explains error compounding. Yeah, because in this case, if one word is wrong in the beginning itself, all this has a cascading effect or a compounding effect. Yeah. So we need to ensure that error compounding does not happen. Where does the error actually take place, and how do we simplify, or sorry, prevent those errors downstream? Yeah. And which is why the fix is always upstream. You need to ensure that there is better grounding and tighter context sharpening in the beginning itself. So if your prompts are not good and you have not given proper context to the system, the distribution that gets generated will also not have proper output. And the four words that we said we will discuss about: prior, exterior, posterior, likelihood, evidence, all comes here. So prior also is called the base rate, as in the previous one, how likely the hypothesis was before you saw any evidence. That's what base rate does. It's a probability calculation. Okay. So likelihood, how likely this evidence would be if the hypothesis were true. That's what we are trying to calculate with likelihood. Posterior, post our belief has been updated. Your updated belief and the thing you actually want. Evidence, we know it is a normalizer that makes it all sum to one. Yeah. The one line intuition that we are trying to say is, hey, new belief is proportional to old belief times or multiplied by how well the hypothesis explains what we just saw. Because it's a probability, we are trying to multiply it. Yeah. Why this naming matters is, in a review we will need to say, hey, which one is missing from somebody's argument? Was it the likelihood, was it the posterior, was it the prior, or the evidence? Yeah, 9 out of 10 it is the prior. Because how likely the hypothesis was before you saw any evidence, before evidence collection, how likely hypothesis was already there. Yeah. And if we cannot name all these four parts out loud, we cannot spot which one is a vendor has quietly left out in their pitch. Let's do a calculation that will help us understand the importance of this. Imagine there are 1 million items per day that need to be detected for certain violations. And violations are only 0.1%, that is 1000. In a million, 0.1%, not even 1%. 1% would have been your 100k. sorry, 10% would have been 100k, 1% would have been 10k, so 0.1% is 1000. Yeah. um, so detector 99%, and which is 99%. Okay, so we are catching 990, we are only leaving or missing the last 10. So how many get cleared? If you subtract 990, we get 989,010. Yeah, and wrongly flagged values from this 1000. Sorry, in the 10%, if you remove the 10, which is 9,990. So what we are saying is, we look at the two error columns, 10 missed violations, okay, and 9,990 false alarms. This is false positives, yeah, and it's 1,000 times larger. So 1% error rate on clean content swarms a 99% catch rate on violations. This is like the recall, guys. If recall is not right, you're gonna make a lot of mistakes there. And that's what we are saying. Hey, 980 plus this one gives you 10,980, and the real is 9,990 by this, which is 9%. Yeah, so the probability of violation given flagged is 9%, even though p of flagged given violation is 99% accuracy. Yeah, that posterior has a name that we already used. Yeah, it is precision arriving properly in week 11. We'll look at this when we come here. Yeah, and what a principal product manager or even a product manager should ideally do is ask for the base rate, which is prior, before you ask for accuracy. Refuse accuracy as the headline metric for rare events because it does not cover them. like like we earlier saw, averages are a very bad metric. Rather, we should look at percentiles. Similarly, we should reject accuracy or deprioritize accuracy for our base rate or prior. And we need to look at the size of the review queue as well, because there will be a lot of false positives, and just accuracy will not help us identify that. We need to raise the effective base rate by cascading, because there is a compounding effect. We need to ensure we are doing the right evaluation. Move the threshold deliberately. And that brings us to the last section, which is sampling and the softmax. This is how we understand, hey, whatever being given out is not the token, it's a list of values for probable words. And when we do the sampling, we pick certain words based on the cutoff or threshold that we put using top k, top p kind of a stuff. So how does that happen is what we are going to look at. During decoding, what happens is the final layer produces logits. When we say logits, is nothing but numbers. Logit functions enable or disable a certain value, and there is a associated probability. Yeah. So one raw score per vocabulary token is generated. Yeah. They are unbounded real numbers that we know. They can be negative. They can be 14.7. So they don't mean anything. To put them in a construct or limit them in a certain size, we do softmax, because that will put them in the scope of 0 to 1. Yeah. And two design choices worth knowing is the exponentiation makes everything positive and amplifies differences. A logic gap of 2 becomes a probability ratio of about some. Forget all this, is not required. Softmax is not a gentle normalizer because it is very opinionated. It very strongly puts everything between a 0 and 1, the output. Yeah. So it produces a valid distribution. Valid is not the same as truthful, as in it only says I'm confident about these values in a particular gap. It does not say whether the words are really important. Yeah, that's a normalization of arbitrary interval scores, not a readout of belief. So imagine logits are 3, 1, 0.2, and so on. If you take their exponentials, this values, they sum up to 25.c. But if you calculate their probabilities, they come like this. Some of these comes to 1, 18, 90, 94, 99. And if you sum the rest, it's almost 1 as a score. Yeah. the probability of the first logit is 80%, second is 10%, and so on. That's what we are trying to say. Yeah, instead of these logit numbers which do not make sense, we calculate their softmax values and then we produce it. So the model produces this distribution, the decoder picks, yeah, the decoder picks this every argument about the temperature top p, and determinism is an argument about the second step, not the first. So how deterministic do you want to be depends on how many values will you pick from this distribution. Will you pick only one, which is 80%? Then it becomes very deterministic. But if you pick all the four, then there is a creativity end that is left in the sample that you're picking as the words. So if you want more creativity, pick as many as possible, as many p's as possible, top p's. If you want very deterministic answer, pick a little, very few words. And that's what the temperature is shaping the distribution. That's all we are trying to say here. The sentence to retire from your vocabulary is lower the temperature so it hallucinates less. No, it does not. Actually, this is wrong. Actually, and correcting it is a credibility moment in a review. Temperature changes how you sample from the distribution. The model already produced. It does not change the distribution's contents. When we set temperature, it will tell how many words to pick up. The yeah, the temperature reshapes the distribution that we were looking at. The logic functions have got the top performing tokens. The tokens are distributed with are shown confidently with certain probabilities, and the decoder picks certain tokens and gives us an output. So what we are trying to say is temperature zero is the model being predictable, not the model being right. As in, it only picks what elements to take, but the token has already been picked up. So being right or wrong is not being decided by temperature. It is only picks how creative can be with more tokens, or different types of token with lower probabilities and so on, or how deterministic can be with limited number of tokens. So temperature only controls uh, the the creativity or uh, freedom to show more variety of data rather than the truthfulness of the data. And that's what we are saying. We need to retire from vocabulary. Lower the temperature, it hallucinates less. No, hallucination has already happened. We are only showing how creatively you are going to see that answer. Yeah. So if the model puts real mass on a false statement, top temperature zero picks a false statement every time. Even with zero, temperature zero, which is very deterministic answer, it can always pick a wrong statement always confidently. So giving you a confidence of 99% does not mean that the statement is correct. It only means that system has picked certain tokens with these probabilities. Yeah, that's what we are saying. Yeah, the one line. Temperature is a diversity dial, not a truth dial. If someone reaches for it to fix accuracy, they are treating a symptom with the wrong instrument. They are diagnosing it wrong, they are giving a wrong fix. So, truncation of top K, top P. Top K says that, hey, pick only the first two elements. That's top K, how many number of elements. Top P says that pick all those elements whose probabilities add up to a certain number. That's all top P does. Top P adapts two tokens whose confidence is 200 when uncertain and so on. Yeah. So top K is the top number of elements. Top P is sum of those elements, top elements whose sum comes to a particular score. Here in this case, if you want 0.9, 5, 6, 7, 8, approximately 9, and maybe you add D, yeah, just to cross it over D, yeah. So why does the same prompt give different answers? That's purely of sampling. Yeah, it's not because of temperature. Temperature also is a reason, but primarily because of sampling. Yeah, any temperature above zero draws randomly from the distribution by design, and it happens. The model or system changed under you. The principal level marker is we need to understand that, hey, PM who answers only with the first one sounds informed. Yeah, names all three sounds like they have shipped. The model or system changed under you. The floating point and batching non-determinism is there. Your sampling is also there. Yeah, important is this floating point and batching under non-determinism. Yeah, even at temperature zero, GPU kernels sum in non-deterministic order because floating point have too many numbers. You know, they go on to so many of decimal places. So due to rounding of characteristics or some other characteristics, when they are picked up, they could be picked up totally differently as well. And that's interesting, the way we looked at this, because log probabilities and the confidence trap are all living there. Yeah, multiplying hundreds of probabilities underflows to zero because they are always in 0 point something something. They always underflow to zero. So a system works in logs, ensuring what needs to be surfaced is always surfaced. And when a provider exposes log probes, uh, we get a per token confidence signal, and that's what we need to always uh, track or look for. But this trap is sharp. That is, the model's probability is not the probability of being correct. Yeah, whenever a model says that, hey, I'm 98% sure, it only means that it has collected these tokens correctly. Yeah, it does not say whether the data is correct. Yeah, so the confidence trap is living there. Yeah, we need to understand that. And that gap is calibration. How do you calibrate the model such that it is right 70% of the time? Yeah, on things it says 70% about. Yeah, typically they are always overconfident LLMs, and that's why we need RLHF to make it worse and make them very grounded in nature. And that brings us to PM pass, where we looked at many ideas. We need to understand how we as product managers take a decision and win over that. Yeah, so we looked at each concept. When where it landed, we understood this. Yeah, we said distribution versus point estimate. Distribution is different, which is the mean of the point estimates or points that we took from the sample and we distributed. Typically, if they are good enough, they'll always become Gaussian in nature or normal distributed. And your latency, SLAs, cost budgets are always calculated in percentile, never in means. Yeah, we will carry this forward. Track D, part 9 will cover the cost. Track C, part 14 will look at observability, all from this angle. Your base rate, which is your prior, yeah, the probability of prior from the Bayes theorem. We looked at, hey, how we are queuing the sizing, the threshold setting, cascade architecture. All this product decisions are coming from these base rate and bias. Yeah. um, part is 11 Part 11 of track A will talk about precision, precision recall and all. We'll look at that. Your part track D, part 6, will look at golden data sets for evals as a AI PMs. How we do that are all based on this. Your chain ruling and conditional, while we already saw this, we are going to see it in C7 also, track C, C7, and track B, B12 also. We are going to look there. Yeah, the prompt and context strategy, why error compounds, all is because of chain ruling. Yeah, so softmax and temperature settings, because of the variety of answers that we get are dependent on this. We need to be very sure of how do we configure them to get the right outputs. So per surface decoding configuration is required. Every layer in the whole pipeline or workflow needs to have its own decoding configuration, and we understand where something goes wrong, because if errors are compounding, where could we have gone wrong, that we need to understand. Yeah, so support bot versus ideation tool both require different types of temperatures. Ideation tool requires a higher temperature for creativity. Support bot requires a lower temperature. Calibration, whether you may show a confidence number at all, depends on this. In the UX that we discussed last week, ideally we should show the confidence, but is it helpful in that context? It what we need to understand. Multiple places we are going to see this. Error configurations we are going to see this. D7 responsible AI we're going to see this, and so on. And this decoding policy is actually a product spec. If you don't layer it in, you will not or build the traceability. You will not understand how a system gave a particular answer. Yeah, support answer bot. If the temperature is 0, it's very reproducible, auditable, compared. But if there is ideation or brainstorm, we give higher temperature. Diversity of the value is given to the user. How they use it really becomes outcome of this. The structured extraction from a particular document, it has to be very crisp, so we give the temperature low. Any deviation is a parse failure, it looks like a hallucinated value. Marketing variants, 1.1 above 1 also, because we need different variants, creative ads, creative marketing campaigns, and so on. Yeah, so more the samples the better, human becomes the filter there. Monte Carlo and what it costs, we'll see this in one of the future sessions. I'm not going to cover it here. When to choose high variance on purpose, when you require very creative answers like marketing, brainstorming, mind mapping, any of that tasks, you need creative answers. Traps to correct early, because these are misconceptions. 95% confidence means it is 95% right of the time. No, that is calibration. Yeah, that's not confidence. It has to be measured, and LLMs are typically overconfident always. Temperature 0 stops hallucinations. No, it does not. It only stops the variation of answers the next time it generates an answer. It does not stop hallucination. Top guarantees identical outputs, not really, because if the model is shared on GPU infrastructure, the floating point calculations and batching will still result in non-deterministic values which can flip near tie values. So maybe 90% of the values will, or outcomes could still be same. It's again very probabilistic. How we need to look at how the model is spread across the GPU infrastructure. 99% accuracy is a good metric only if you know the base rate or prior. The prior is before you knew something could happen, what was the base rate. If you can calculate that, 99% accuracy can be measured as a good metric. Average latency is within budget. Averages hide inside heavy tails, P99 and so on. So we need to understand percentiles rather than average latency. Yeah, or we are describing a user who does not exist. That becomes the measuring criteria. Independent events, so we can just multiply. If they are not related, we can add them, not multiply. Most production failures are correlated. They are not actually independent events, they are dependent events. Softmax tells us where the model believes. No, Softmax is a normalization of arbitrary internal scores. Yeah, what it does is it produces a valid distribution, which is not the same as a truthful one. It helps you pick the right values. It does not help you stop picking the wrong one. More samples always means a better answer. No, because we saw why. So, and here are some questions that are going to be asked in the interviews. Yeah, why is a language model non-deterministic, and how would you fix it? There is no fix. It is going to have some non-determinism always. We can reduce the variance, but we can never avoid it. Yeah, and that's why large language models, we understood very recently that hey, generation is sampling. We use the temperature to control how much top p or top k values can be taken, and using that we can reduce the variance, but it can never be reduced to 0. So non-determinism will always be there. What we could do is reduce the temperature to 0 to or plus a seed initial data that we have, put a seed number there always. Maybe that will reduce it to very close, but it cannot be completely eliminated. A vendor says the moderation model is 99% accurate. What next? I should typically ask for the base rate or the prior. Hey, at a 0.1 prevalence on a million items, you get 990 true catches. False positives are there, so the 9% of the queue is real. I want the precision and recall of the operating threshold. That's what we should look at. Calculate the F1 score or look at the confusion matrix. Yeah, and then imply what the daily review volume will look like, because that is a headcount number, not just 99% accuracy. Explain temperature to a non-technical executive in 30 seconds. Ideally, I would start with saying, hey, model never picks one particular answer. It ranks multiple answers and it gives a probability all of them. Temperature controls how strictly we obey that ranking. At 0, we are taking the top word and rest of them are discarded. But with higher temperature, we pick the lower ranked ones also and give them a a certain chance, and that's why there is a diversity at the bottom, closer to one. So temperature is nothing but a diversity dial. We are controlling and saying how diverse can the answer be. It's not a correctness dial. Mean latency is 900 milliseconds and SLO is 1 second. We're going to ask, hey, are you fine? I do not know yet, and I would push back on the framing because latency is heavy tailed towards the end. So we need to ask for P95 and P99 scores as well. Understand, is the P99 greater than 8 seconds? 1 in 100 requests is a terrible experience. A couple more questions. Where does the chain rule of probability show up in a LLM product? We understood because all these models are autoregressive models, and once we compute them towards the end, the probability of each token is calculated based on the probability of the previous token. Yeah, so the if the first token itself was incorrectly uh, determined or uh, probabilistically generated, rest all will be wrong. So our prompt, our retrieved context are all um, values. They are conditions based on which our next token is being predicted. So the error is gonna only compound towards the end based on our prompt and the retrieved context. So we need to ensure that this chain rule of probability, which is a typical compounding framework, needs to ensure the first few words are correct in the sequence. If not, we are going to see everything wrong. When would you deliberately choose a higher variance confidence? When we want more variable answers or varying answers, and it's for more creative efforts like marketing, brainstorming, naming, synthetic test cases, all of these. If you want to do any of them as creative tasks, we need a higher variance, a higher temperature. Now we have understood all this. What is expectation? Yeah, the long run average weighted by probability, the variance spread around the mean, the heavy tail, most values live there, long tail values of large ones live there. So latency and cost could actually heavily sway the whole answers. So ask everything in percentiles, or don't ask at all. Don't ask in averages. Yeah, base rate, the priors, how common the thing is before any evidence was ever collected. That's what we are trying to answer here. Accuracy without a number is a marketing number. We looked at posterior, we looked at softmax, we looked at temperature, we looked at calibration. Yeah, and that's track a part 4, where we are talking about the probabilistic bias and sampling in the softmax. What we are saying is the LLMs output the odds, somebody else decides the bet. The sampling is deciding the bet, not the LLM has given certain token predictions. The decoder, where the sampling happens of top K, top P words, that decides what the outcomes are.